This is again a reenactment of a talk that I gave a day or two ago because the recording failed. So, first I want to say thank you to Rajat for inviting me to be part of India's National Science Day. So what I want to talk about first is quantum mechanics and classical mechanics as if they're dataset formalism. So they're not about particles, their properties, ensembles of particles, anything of that sort. Once I've talked about that for both quantum mechanics and classical mechanics, then I'll specialize to quantum classical mechanics in particular and show how that motivates us to construct something that's more general than classical mechanics, what I call CM+, where we use the Poisson bracket to introduce noncommutativity, and we also introduce something different from thermal noise, quantum noise, with different symmetry properties. Because there's noncommutativity in CM+, that means there's also a measurement problem for CM+, just as there is for quantum mechanics. And because we've added quantum noise, that difference between quantum and thermal noise is one of Lorentz invariance, and that requires us to work in 1+3 dimensions. And so we should be working with field theories, and particularly with a noisy classical field theory that has two kinds of noise, thermal and quantum noise. So more complicated than just the heat equation, for example. So then particularly we'll talk about the Bell inequalities for a noisy classical field as a way to transition to the second part, which will be to discuss quantum field theory as a signal analysis formalism. So I'll start by thinking about quantum field theory with signal analysis in mind, and then show you how we can construct within quantum field theory a noisy classical field, what I call quantum non-demolition field theory. And one can find a starting point for this in an article by 𝐏𝐚𝐫𝐭 𝐈 in PRX 2012, where quantum mechanics free subsystems essentially is what they call a classical noisy field. Now there's a part 3 that I won't talk about today because it's based on something that's not published. All the rest of the part 1 and 2 is based on published work. So here's a rudimentary schematic in which we have a region here that we want to know something about, and so we surround it with many devices, each of which is connected by a signal line to a piece of hardware which analyzes that signal in real time. So the signal is noisy, but it's not so noisy that there aren't distinct times which we can identify as events. So when we do identify an event, we store in a very compressed way something about the signal, just the time at which the event happened. Once we've got lots of recorded data, then we'll do a data analysis of that after the fact. We'll write a paper, we'll submit it to a journal. Hopefully people will find it interesting and use the ideas. Now, one aspect of this schematic is that from an engineering perspective, the only place where we actually measure the electromagnetic field, the currents and the voltages really, is these points here where the hardware, where these signal lines go into the analysis hardware. But we have centuries of experience so that we can compute what we would think the electromagnetic field might be within these devices, or indeed what they might be within a device if we had put the device there in some different place, even though we didn't. So from an experiment, we obtain data sets. Those contain lists of numbers. And so for those lists of numbers, we can compute the average values and relative frequencies of the different data values, and also higher statistics like variance and so on. So something in the theory should generate expected averages, etc., for future data sets, so that we can confirm that the theory is correct to the data sets we gather. We can include other theoretical objects, particle properties, anything else that you think is interesting that actually helps you intuitively understand what's happening within the apparatus. But those things are, in a sense, extra. People are important. People decide what experiment they want to do. They find the money to build the apparatus, and then they turn on the power, and they become really very unimportant. They can go for coffee on the moon. They can believe that the moon is made of green cheese. It will make no difference. It will make no difference if I turn on the power or someone else does, and we have completely different beliefs about what happens inside the apparatus. Nonetheless, the data will be the same, more or less. And the data is collected at gigahertz rates, furthermore, so this is something that I personally do not work at gigahertz rates. Once the experiment is finished, then people become important again. They decide what computer programs they should write to analyze the data. They write an article about the experiment, and then they decide what experiment they want to do next, and so it goes. My focus will be very much on the gigahertz rate data, not on what people do, drink the coffee, and so on. So now to start with an elementary and very concrete matrix model. If we have a measurement M, for which the data values are just a list of values, M1, M2, and so on, and for each of those values there's a relative frequency, P1, P2. So the weighted average of those measurements, those data values, is I'm just going to write as rho applied to the measurement operator, M hat, which as I'm going to write it, and that just should be this expression here. Now that we can write as well in terms of two matrices, for which we have the measurement data values down the diagonal in one, and for the other we have the relative frequencies down the diagonal. And it doesn't matter what the values are to here, because the zeros will cancel them out when we take the trace. We get this expression, where we require that the density matrix, as we would call it if this was quantum mechanics, it must satisfy these properties so that the numbers we get for relative frequencies satisfy the rules we expect for probabilities, for example. But now if we have a different measurement, M prime, for which the matrix is diagonal in a different basis, then we can use the same rho hat, but now because it's a different basis, this matrix with the M1 prime and so on down the diagonal will pick out a different set of values down the diagonal in that basis, even though we're using the same matrix, the same density operator. So we get this expression. So what we've done here is we've constructed a single formal structure that contains many different probability spaces, as the mathematician would say of this. This is purely mathematics. There's no physics in this construction. There's no H-bar. It's just a matrix model of what a mathematician would call a generalized probability theory. They used to call this a quantum probability theory, but around a few decades ago they started calling it generalized probability. So for traditional classical physics, we use different initial conditions for different contexts. So we have a particular initial condition here, and we can evolve it backwards and forwards in time using a differential equation. And we can use the same differential equation for a different set of initial conditions and move it backwards and forwards in time using the same differential equation. What operator algebras give us? It gives us more tools for modeling many experiments all at once. We can put all of those initial conditions into a single structure, and we can move that backwards and forwards in time using a unitary transformation. So that is the case both for classical and for quantum mechanics. We can do that. For quantum mechanics, we know it's useful. There's no reason why classical mechanics can't use that kind of integrated many initial conditions sort of initial condition. So, to be a little more formal, to discuss algebraic quantum mechanics and classical mechanics, for which there is some things in the literature, but mostly not. So we're going to begin, as we did on the previous slide, taking a linear operator to correspond to the data values part of a data set. So we have a diagonal matrix representation in which the data values go down the diagonal. And that we do instead of saying, as the first axiom for quantum mechanics very commonly is, to say that a Hilbert space corresponds to a system, which is a much more theoretical statement than this very much more data-driven approach. So now we have these abstract measurements, and we can add them and multiply them, because after all, we want to make contact with quantum mechanics. So we have a data set and its data values corresponds to a linear operator and its eigenvalues. And that also we can think of as corresponding to a random variable and its outcomes. And if the algebra is non-commutative, we'd say it's quantum mechanics. If it's commutative, we'd say it's classical mechanics. And then we have this set of four properties which are really pretty much standard for in elementary matrix algebra and indeed operator algebra. So now that doesn't give us any information about the expected data set averages. So we introduce, as on the previous slide, a state rho that maps those measurement operators to the expected data set averages when or if we collect data. So we have the expected value for the measurement for the data set M1. And the nice thing about this formalism is that we can write down the probability distribution for M1 purely in terms of a Dirac delta function applied to the M1 with the number u. That gives us the probability distribution. We can take the Fourier transform of that to give us what's called the characteristic function. And I'm going to use j as the imaginary because I want to really think like an engineer for the purpose of this talk. Now, there's a standard set of four rules that are satisfied by a state rho that very much map onto the standard rules for relative frequencies, because we want relative frequencies out of this formalism. So, because relative frequencies are positive and normalized and real valued, we have correspondingly these three equations as well. And because we can add relative frequencies, we have von Neumann linearity, so that even if A and B do not commute, nonetheless we have this expression is satisfied. So now the nice thing about this construction, this choice of the rules for the state, is that it means we can use measurement operators to modulate the state rho. So this structure also satisfies the rules for it to be a state as well. And we can construct many such states once we have a suitable sized algebra. And this is the basis of the 𝐏𝐚𝐫𝐭 construction, as mathematicians will call it, of a Hilbert space. So now, even though we started out without a Hilbert space, by proceeding through what we want to achieve for this physical model, we've reached a Hilbert space, slightly slower. We've gone in sort of the opposite direction from the usual ways we construct the axioms for quantum mechanics. The structure, the GNS construction, also lets us think of a state applied to a measurement operator as a vector and its covector bracketed around a measurement operator, and similarly for a modulated state. And you'll notice that by saying modulated, I'm really starting to try to push us towards a signal analysis kind of way of thinking. So how does this work for algebraic classical mechanics in particular? We take classical mechanics very commonly to be an algebra of functions of position and of momentum, so on phase space as that's called. This has three binary operations, however. This is not the usual high school algebra. It has addition and multiplication, those are straightforward, but the Poisson bracket as well makes this much more complicated. Now we can construct a simpler algebra of transformations that just has two binary operations of addition and composition by introducing two operators, multiply by W and just the same Poisson by W, using the multiplication and using the Poisson bracket in exactly the same way to construct these classes of operators, the YW operators and the ZW operators, multiply by and Poisson by W. And then we can work out fairly straightforwardly that the commutation relations for those operators is given by this set of equations here. So now, just to give an indication of the kind of thing that the Poisson bracket does for us in classical mechanics, Poisson by the Hamiltonian function gives us a generator of time evolution, Liouvillean operator, and so that takes a particular position in the phase space and moves it along a curve. And for Poisson by W, we get something very similar, except that instead of along the usual dynamical curve that's given by the Liouvillean operator, the W transformation moves us along a different curve. So each Poisson by operator gives us a different set of curves. So what I've been suggesting is that we can use the Z's as well as the Y's of something that's more powerful than classical mechanics, and so I call it CM+, so long as we're willing to use these ZW operators without any restriction. And I'll show you in a few slides' time what I mean by that. And that gives us an algebraic measurement theory that's shared with quantum mechanics. It includes noncommutativity, measurement incompatibility. And the really nice thing about this is we can have isomorphisms between CM+ and quantum mechanics instead of the usual very much not isomorphisms of quantization and the correspondence principle between classical mechanics and quantum mechanics. So now that was purely an algebraic structure that I showed you in that previous slide. To show you what a state looks like for the general case would be too complicated, so I'm going to specialize to the classical simple harmonic oscillator. And for that, we have the Poisson bracket is just this set of differential operators put together like this, and multiplication by Q and by P is straightforward, of course. The Poisson by P and Poisson by Q operations, though, those become just derivative operators with respect to Q and respect to P with a minus sign in this case. And so we find for the commutation relations for these objects, we have these two copies of what's called the Weyl algebra. We also have, for the Hamiltonian function, we have this half q squared plus p squared, and if that's constant, then that's just the equation for a circle in phase space. And then we have the Poisson by h, and this is this differential operator moves us around a circle. So that's the relationship between the Poisson operator and the multiplication operator. So now for a state, the natural place to go is the late 19th century, where one finds the Gibbs thermal state for a simple harmonic oscillator at a temperature kT is just a normal probability distribution. And so we can write that using the Dirac delta function formula, as I showed you earlier, and it just is written as this Gaussian expression. We take the Fourier transform of that probability distribution using the YQ and YP operators as measurement operators as related to a data set. And then we have the engineer's imaginary J, which gives us this equation just as the Fourier transform of this. But now, because we've got the engineer's imaginary J, we now have the Weyl-Heisenberg algebra, and so it's natural to use raising and lowering operators just as we do in quantum mechanics. But we use KT instead of H bar, so this is very much not quantum mechanics, this is a purely classical construction. We construct the Poisson operator in terms of a difference instead of a sum, and then we have this relationship as usual, and then we say that the lowering operator annihilates a thermal vector. And that allows us to compute as well for the Poisson operators as well as for the multiplication operators what the probability distribution will be for that, or rather the characteristic function. So we can also construct modulated non-equilibrium states. And so that gives us a thermal Hilbert space, which is entirely classical. So instead of trying to map classical Q and P to a quantum Q and P, which doesn't work, we can instead map Q and J partially Q to Q1 and P1, quantum Q1 and P1, and that is an isomorphism. And we have similarly for P and J partially P. But, crucially, KT is not H bar. Thermal noise is not quantum noise. It can't be, because the history of the 20th century would have been completely different if it were so. So what is the difference? The first thing to notice is that H bar has units of action, whereas KT has units of energy. So different units, but that doesn't give us any real clue as to what we should do next. But if we look in quantum field theory, we realize that the quantum vacuum, quantum noise, is Lorentz invariant, whereas thermal noise is not invariant under Lorentz boosts. And this is a difference of symmetry properties, so this goes deep. And that can be used in CM+ perfectly well. And once we do that, then we find that H bar is the amplitude of a Lorentz invariant noise, and KT is the amplitude of a less invariant thermal noise. So this gives us two different kinds of noise, always acting together, but also separately in a way. So this gives us a new reason, however, to think we must work with field theories, because indeed we can only define the Lorentz group in at least 1 + 1 dimensions, and of course we'll want to work in 1 + 3 dimensions for the most part. So from now on, when I say CM+, I actually mean a field theory with a Lorentz invariant noise with amplitude H bar. We should note as well that for CM+, we have that the H bar approaching 0 is no longer a classical approximation, because CM+ is perfectly happy with a non-zero Lorentz invariant noise. Nonetheless, it's a mean field approximation that we'll want to use whenever it's possible, just so that the mathematics comes out rather simpler. So CM+ can and should include noncommutativity and quantum noise, and that gives us a measurement theory, a Hilbert space construction, that is exactly the same as for quantum mechanics. But there is a more technical difference, which is that for quantum mechanics, the Hamiltonian operator is bounded below. And that gives us analytic properties that are very useful whenever we're doing quantum mechanics. In contrast, for CM+, we do not obtain that analytic structure. So analyticity, even though it's mathematically useful, we're not going to include in CM+, partly so that we have two different kinds of description we can use for the same apparatus. And we can say that quantum mechanics is an analytic form of CM+, but they're just two different kinds of description of the same apparatus. And of course, the apparatus does not care which description we use. And if you know signal analysis, then you'll know that this is very like using the analytic signal for the quantum mechanics case or the real signal for the CM+ case, and that's why I suggest this naming of quantum mechanics as an analytic form of CM+. So classical mechanics has really had its hands tied behind its back. For classical simple harmonic oscillator, we're allowed to use ZP, just partially Q, to generate translations. If we expand out this expression, we find that it's just to subtract a constant from the multiply by Q operator. And that is taken to be perfectly reasonable by everybody. But we don't allow ourselves to use ZP cubed to generate a unitary transformation by using exactly the same structure, because that results in the subtraction of a differential operator from the multiply by Q operator. And so people have taken that to be very different, except, of course, that quantum mechanics is happy to use 𝐷𝐵³ to transform to a different experiment. And that can be useful in the same way for classical mechanics, and that's just what we saw in the elementary matrix model on slide number 5. If we allow ourselves to unlock that superpower for classical mechanics, the idea of what an initial condition is becomes more complicated, because now we have to discover many, many different initial conditions to determine what the initial condition for CM+ is. But that's something that we're used to doing for quantum mechanics in any case. And it's useful when we do that in quantum mechanics, and there's no reason to think it won't be useful for CM+ as well. So having introduced noncommutativity into CM+, it has a measurement problem just the same as quantum mechanics does. And I found this helpful for rethinking the measurement problem for quantum mechanics. And so I'll discuss what I'm going to do now is I'm going to discuss inside quantum mechanics, but always with CM+ in the background. We have two measurements, A and B, that have different sets of data values that arise when we do measurements we do that measurement. Then we can write the measurement operator that we would use for that as the sum of those measurement data values and a product with projection operators, where each P1, for example, has just a 1 in this top diagonal entry, and so on down the diagonal. Now for a measurement of A, where we have the state vector psi, we obtain the result alpha m with a probability that's given by those projection operators. We bracket the vector psi and its covector around the projection operator. And for simple cases, this projection operator is just a shorthand for this operator, and so we find that this is just, in that case, is just this expression, which is, of course, the Born rule. But now if we want to do two measurements, we're going to do A first, and then we're going to do B. We say that the result alpha m collapses the state vector. So we have psi becomes psi m, which we construct by just using the projection operators again, and we have to normalize so that we get, again, something that will give us probabilities, relative frequencies. And this is called the Lerder's rule. Nothing new here at all. Then we measure B in that state. So we obtain the result alpha m followed by beta n, and that's just a conditional probability. We can compute it just like this, and we can expand this out to give us this expression, using this one above, of course. So now the joint probability is just this very straightforward expression where we've used the probability P over alpha m to get this expression. So now we have this joint probability, and indeed these operators here are positive operators, and they are and have to be so that these numbers are always positive. And those generate the joint probabilities for the results alpha m, beta m. So instead of collapse affecting a state, we can take collapse to affect the next measurement. So instead of using this expression here to try to compute probabilities, which won't work, it will give you complex numbers, or it may give you negative numbers or numbers greater than 1. We instead use this structure, which is exactly the same as the JMN. So we've modified the QN to make it into this. That works very nicely to construct what I call a collapse product. A collapse B with data values that with the data values you'd expect, and we can do that even if A and B don't commute. But now this is just a joint probability. That's something which we usually would say is classical. And indeed we can use commuting operators A prime and B excuse me, A prime and B prime, and a different state vector state psi prime in a different Hilbert space H prime. So if we changed everything, and we can make the Hilbert space as big as we like, and we can make it as big as is necessary to match the values we got from the original quantum expression. Now this seems a little bit of a cheat perhaps, but mathematically this is just to use the 9-mark dilation theorem to construct a joint measurement AB that is the same as A collapse B, and indeed it works by introducing a larger Hilbert space. And this is, I think, a useful alternative to decoherence, as we'll see now. So for all practical purposes, of course, decoherence works well enough that physicists routinely consider the measurement problem not to be a problem. But it's interesting to look at what decoherence does. Decoherence takes a large Hilbert space model for whatever's measured, together with whatever measures it, and then shows that environmental noise will very nearly collapse the state to an after measurement state. And it works. 9-mark, on the other hand, is a rather different kind of approach. It takes a small Hilbert space, model for whatever's measured, and then constructs a joint probability for consecutive measurements. It takes a model for a measurement device in a larger Hilbert space in the context of earlier and subsequent measurements. And this is something you can find in the literature since 20 or 30 years ago, and that is often called the principle of deferred measurement. So 𝐼 constructs a rough model and then refines it as needed. And that's what engineers in particular always did, and even classical physicists will do that mostly. If the data sets we don't tell us enough, then we should get more data to analyze. So we can use decoherence or 𝐼, whichever seems easier, more appropriate for whichever particular experiment we're trying to describe. But there's one place where when we're considering signal analysis, it really is easier to use the no collapse, the 𝐼 sort of picture. Because for signal analysis, there are many measurements at time-like separation, where we take the first measurement, we do a collapse, second measurement, do a collapse. So we have hundreds of millions of collapses, possibly. But we can instead use all commuting operators and no collapses to make sure that we just derive the same joint probability for these these different pictures of the same joint probability being the end result of the calculation. So, although we can think of collapse as a dynamical process if we like, it's a perfectly good way of thinking about it, we can also take it to be a joint probability algorithm. So now, as I said earlier, we now have two noises, and it's a classical field because those noises are separated by Lorentz invariance symmetry properties, So I'm also going to think in terms of signal analysis as something of a cognate to classical field theory, not in terms of particles, not in terms of particle properties. If we think about particles, we tend to think of them going down through an apparatus and maybe bouncing off the walls a few times. That's a completely different kind of idea about what's happening within the apparatus than it would be if we think in terms of the heat equation, where boundary conditions matter very, very much to the final solutions we might have for the equilibrium state or for non-equilibrium states within the particular apparatus. So what this schematic is from an experiment from the mid-1990s by 𝐏𝐚𝐫𝐭 𝐈, and he has this beautiful schematic that, for one thing, says he has a central pump. He doesn't talk about shoveling particles into the apparatus. He talks about pumping and modulating the ground state of the apparatus, the electromagnetic field, the noisy electromagnetic field within the apparatus. And he modulates it very, very carefully so that the silicon avalanche photodiodes here and here, Alice's and Bob's as we usually say, there are correlations between what happens at those events that violate the Bell inequalities. And as well as these two APDs, both Alice and Bob have an electro-optic modulator that modulates the electromagnetic field in a particular way depending on the bit that is generated by this random bit generator. Now, another really nice thing about this schematic is that 𝐏𝐚𝐫𝐭 is very clear about what he stores. He stores the time at which an event happens in one of those two APDs, which APD it was in, and what the setting of the random bit was at the time of that event. So when 𝐏𝐚𝐫𝐭 gets some experiment measurement results, Alice sees almost 400,000 APD events in a 10-second period. And every single one of the more than 15,000 coincident event pairs, where Alice and Bob see an event within 3 nanoseconds of each other. So this is plus or minus 3 nanoseconds. This is 0 to 10 seconds. So there's a factor of 1 billion between the two axes. As you see, there are many coincident events, really, and that's already a little bit of a surprise, although it's not too difficult to explain that in classical mechanics. But also, the majority of the events are green or yellow in the color scheme I've chosen up here, where the red is the diagonal, where the 2 bits for Alice and the 2 bits for Bob are the same, and so for the other 3 diagonals. So if we take that graphic and turn it on its side, and we take 100 vertical slices through that, and we count up the number of each of the 16 different events for each of those slices, then we obtain these 16 histograms. Then we add up the number of events in each of those in each of those histograms to get 16 numbers, which we feed into a by now standard calculation of the violation of a Bell-type inequality. So what we've done here is we've taken a completely classical set of data, we've applied a completely classical algorithm, and we've obtained a number for which classical mechanics says this is not okay. Quantum mechanics uses non-commuting operators to model the violation of Bell inequalities perfectly happily. This is a tradition in the literature you can find since around about 1980. Classical mechanics, however, has only commuting operators, so it's computationally incomplete, I suggest we should say. Quantum mechanics is often said to be incomplete, but this is to say that classical mechanics is computationally incomplete in this specific way. But we have added non-commutativity into classical mechanics, into CM+, and that's just the use of Hilbert spaces. And non-commuting operators is natural for that. And so CM+ is completely unmoved by this computation of the violation of Bell inequalities. What I think we're doing when we construct an experiment is I think we're engineering noise in the whole apparatus, both quantum and thermal noise. We engineer the central device so that when the power is on, distant events here and here violate the Bell inequalities. And indeed, it does that by ensuring, part of what is involved is ensuring that events are coincident. So there are significant correlations, that space-like separation, between the internal degrees of freedom of these different avalanche photodiodes. Now we make sure that electro-optic modulator settings from the two random bit generators are very little correlated, and we could check that they are because we have the random bit numbers that were generated. We can apply tests to whether those are random. But we should expect correlations between the inner workings of the two electro-optic modulators. For one thing, there are correlations between the inner workings of the four APDs, and these are pretty much right next door to these APDs. I think also notice that the electro-optic modulators are designed to act on the noisy electromagnetic field so that the statistics to the photodiodes are different depending on the setting. And so just by a Newtonian idea of action and reaction, we should expect also that the noisy electromagnetic field will act on the electromagnetic modulators. So with those correlations, it's fairly straightforward to show that Bell inequalities cannot be derived, and I did so in an article from 2006. So what difference does this make? I just have a different story about the internals from the story you have. That gives me a different kind of idea as to what might be interesting to do next. And the experiment I would like to see done next, and this is I've been suggesting for the last 5 years, is that if we have the power off, then of course there'll be very few events. But if we turn on the power, then lots of events will appear in Gregor's experiment's case after about a microsecond. But how soon do coincidences happen? And how soon do we observe the prevalence of green and yellow events instead of red and blue events as well? Do events and coincidences in green and yellow propagate in a different way? What changes as we change the distance from a few hundred meters to a few hundred kilometers, perhaps? What this does is this probes non-local propagation experimentally. And indeed, again, if the datasets we have don't tell us enough, then we should get more data to analyze. So, I'm suggesting a new interpretation of quantum mechanics. It changes nothing, except it does change our intuition as to what's happening inside the experiment. It doesn't change what the experiment does. In this interpretation, you can have many worlds or Copenhagen, whatever you fancy, and the experiment will do exactly the same. It does change how we describe and imagine what an experiment does. More importantly, it changes what experiment we think it would be interesting to do next. And I've shown you an experiment I think it would be interesting to do next on the previous slide that you may not think is interesting. So clearly, existing interpretations and textbooks for quantum mechanics still work just fine. What I'm suggesting here makes no difference whatsoever to the textbooks we have. It would be a big mistake to discard centuries of experience that has been condensed into those books about quantization and all that. And indeed, there are no textbooks for CM+, so really it would be a mistake to immediately jump to CM+. But I do have a small suggestion for today. And that is, we usually say, well, we take classical mechanics and we'll change that to quantum mechanics. We'll change classical probability to quantum probability. But I suggest instead, we just say generalized instead of quantum. And that's following the mathematicians who've done that already for probability. I find that just makes quantum mechanics seem less weird, just to say it's generalized mechanics. You may find it different, but I find it helpful. So, the second part. A first look at quantum field theory, and I'm going to nudge us towards signal analysis. If you look at quantum field theory textbooks, you'll find in the first few chapters, for a scalar field, an expression like this, where we separate the operator value distribution, phi hat of x, into lowering operators and raising operator components. Phi hat of x is not a measurement operator, is not something we can use to describe a measurement. But we can construct, and we do construct, what I'll call here an F measurement by smearing, as it's called in the literature, the operator value distribution with a test function. You'll find it in mathematics literature. You also find it called a smearing function because we're smearing the operator value distribution to give us a measurement operator. If you look in the signal analysis literature, however, you'll see it called a window function. It describes how we're looking at the world. F of x tells us where and how big and what shape the F measurement is. So once we've done this, we can now forget this expression here and just work with the F measurement as two components written like this. Now, for quantum mechanics, in the first part, we had measurement operators M1, M2, and M3. But that tells us nothing about the experiment that would get the results we want. We need a description of how to implement each of those measurements. And so we now have two lists of measurement operators and of the descriptions that go with them. So we can merge those two lists together by saying the measurement for the first description, the measurement for the second description, and so on. And that's exactly what quantum field theory does. By smearing the operator value distribution with the test function, we obtain an F measurement, and that just gives us many different measurement operators for which the functions f1, f2, and f3, and so on are just formal and idealized descriptions of how measurements are not point-like. One might be a sphere, another a cube, one might be a rather fuzzy or oval or ovoid or whatever it may be. So from this perspective, quantum field theory is much more like quantum mechanics than we're used to in the textbooks you read about quantum field theory. The only difference is that for each measurement, quantum field theory adds in an idealized description of what the measurement does, or how it does it indeed. So, for the free quantized Klein-Gordon field in particular, where we have the F measurement written as the sum of a lowering and a raising operator, the important thing to know is the commutator between the lowering and raising operator. And we can write that just as a pre-inner product, as it's called, and it's not an inner product just because this pre-inner product can be zero when f and g are both non-zero. And indeed, I'll call this expression the overlap of f and g, because if we make sure that the overlap of f with itself and the overlap of g with itself are both 1, then we find that the absolute value of the pre-inner product is between 0 and 1. Now we can calculate probabilities if all we know is this set of 4 equations. And with that set of 4 equations, we can calculate, so long as the test function is real valued, the probability distribution for the F measurement is just a normal probability distribution with a variance that's given by the overlap of F with itself. So there's the first appearance of the overlap of F with itself as something that might turn up in a physics experiment. And indeed, we can do that using this expression for the characteristic function, which is easy to work out, and then take the inverse Fourier transform to get this. So now we can construct modulated states, just as we did earlier. And that will give us modulated probability distributions. And it gives us a usefully smaller Hilbert space than the full Fock space, which we usually use when we do quantum field theory. And indeed, quantum optics is a field theory that uses only a few different window functions, picks out a particular set of frequencies, perhaps. So I find it helpful to think of the vacuum state as a noisy carrier signal that we're going to modulate. We're going to modulate the probability distributions. And it's broadband because there are many different frequencies. It's noisy because we know nothing about the relative phases for each of those frequencies. So we have, as we saw on the previous slide, the probability distribution for an F measurement in the vacuum state is just a normal distribution centered at 0 everywhere. But now we can modulate that by using this construction, and that results in a displacement of the normal distribution to a displaced value, and the amount of the displacement depends on the overlap of F with G. So we can make sure by using a G function, a G modulation over here that's far away from the F measurement, very little displacement of the probability distribution here, but rather more if the F measurement is closer to the G measurement. So this overlap function determines the geometric structure of a free quantum field in that way. It tells us how a modulation changes measurement results in other places. But we can do more than just displace a probability distribution. We can deform it in really almost arbitrary ways. So for this particular expression, we have 2 humps. We can make sure that there are 4 humps or however many humps we like, and we can change the height of each of the humps, speaking obviously very loosely. So now another thing we can do is we can modulate joint measurements. And that's precisely what 𝐏𝐵𝐵 experiment did. He had, for each of 2 APDs in remote places, he ensured that there were correlations between what happened in those places that violated the Bell inequalities. So this expression here, I'm going to call a Wigner characteristic function because it's only if these measurement operators commute that the inverse Fourier transform of this would give you a joint probability. Otherwise, it will give you something that is not a probability distribution. Now, the reason I introduced that, because it's rather too complicated to go through in detail exactly how that all works in the mathematics, is because it gives us a very effective presentation of the algebraic structure. We have this expression. We can, for the Klein-Gordon field and so on, work out that it corresponds to a Gaussian noise term under the exponential, together with a noncommutativity term that tells you precisely how this structure is quantum instead of classical. Now that fixes the algebraic structure. We can also fix the geometric and dynamical structure in multiple ways. We have for the Klein-Gordon field, we have one version of the overlap function, and for quantum optics we have a different version. Because of time, I won't go through those in any detail. But both of these are positive frequency, which is a result of these projections to only positive frequencies here and here. And they're both Lorentz translation invariant, which they must be in order for us to say this quantum field theory. But now when we look at signal analysis, negative frequencies are not associated with negative energy, so not with instability, nor with backward causality, which is also sometimes mentioned. Because naively, for signal analysis, we talk about the real signal. What we mean is we're working with cosine of omega t, which has both positive and negative frequencies. For the analytic signal, on the other hand, we have only positive frequencies. So it's natural for signal analysis to remove the theta k0 from here and here, and as soon as we do that, we find the noncommutativity term disappears completely. We're left with a completely classically understandable Gaussian noise. So this is a classical, everywhere commutative, noisy classical field theory, but it has not a thermal noise. This has an h-bar scale, Lorentz invariant and translation invariant noise. So this is very much what I was saying about in the previous part of the talk. So now I can show you very specifically how this all works out for what I call quantum optics and Q&D optics. We have this set of 4 equations just as before. And because we're using the pre-inner product, the overlap function on the previous slide for optics, then we find that the commutator for an F measurement and G measurement is sometimes non-zero. But for quantum optics, we can find an involution. So what I'm going to call a bullet involution, which we apply it twice, gives us back the test function, which is what an involution is. And then when we can find that involution, for which this expression is satisfied, then we can construct an FQ&D measurement, as I'm going to call it, for which, constructed like this, which is different from the F bullet measurement, for example, because it commutes no matter what the test functions f and g are. So these FQND measurements generate an effectively classical quantum non-demolition optics field. But the Hilbert space is isomorphic to what we had before because we've used the same raising and lowering operators and the same vector, the same vacuum vector as a starting point. Now I can show you for quantum optics what precisely this looks like, or is rather one example of, because it's not unique. We can project to the left and right helicity components, and for one of those two components we can change the sign. So now this bullet involution is Lorentz invariant, but it's not translation invariant, nor is it local. But both quantum optics and quantum non-demolition optics are Lorentz invariant and translation invariant, and so as quantum and classical examples, both of them are more or less acceptable in a Lorentz invariant sort of world. So now the algebra is generated by these two sets of operators, the FQND measurements and the F measurements, are not isomorphic to each other. But because this is an essentially classical structure, we really ought to say to ourselves, well, we should introduce a Poisson bracket so we can do transformations. And indeed, if we allow it to be unrestricted, then anything we can model with quantum optics, we can also model with QND optics. So we have quantum field theory, where F measurements sometimes commute with G measurements. We have quantum non-demolition field theory, where the QND measurements always commute with any other QND measurements. But for QND FT, we can use generalized probability as well, whenever it's needed. And after all, it's entirely contained within quantum field theory, so any resources that are available for quantum field theory are also available for quantum non-demolition field theory. So this we can think of as quite strongly related to many different things that we might think of as classical, we have thought of as classical. We have for signal analysis, for example, we can add 1 plus 3, we can change from just being a time axis to 1 plus 3 dimensions, space as well. We can add probability theory and generalized probability theory, and we can add quantum noise. All of those things I've shown we can do in a classically fairly straightforward way. We have a similar sort of story for stochastic processes. And then we can also think of this structure as rather like the de Broglie-Bohm construction for quantum field theory, in the sense it gives us trajectories. But this construction is linear, it's Lorentz invariant, and it's more measurement theoretic, which are three reasons, I think, for preferring this kind of construction over what we have from de Broglie-Bohm, without casting any aspersions about that. But this is very much not like superdeterminism. This is generalized probability at all scales. No matter how precisely you measure at 10 to the minus 100 meters, there's always going to be something at smaller scales which is going to prevent you from predicting the future. So I think of this F measurement and FQND measurements as different kinds of idealized measurements, quantum and classical. Now we don't have to be able to actually measure the FQND measurements in order to talk about them. We never could get data for classically ideal measurements if we wanted to know the electromagnetic field at a point within an experiment. We couldn't measure that. We could only calculate what we thought it would be, and that would give us an intuitive sort of idea as to what was happening within the whole apparatus. We imagined and we talked about such measurements as if we could actually perform them. So, what have we done here? We've talked about actually recorded measurement results. So we've adopted something like Copenhagen because we've started with a classical starting point. We've done data analysis to produce statistics. We've predicted future expected statistics. We've focused on the need to know something about each of those measurements. And this measurement description is something that's vital to know. It's what a computer programmer would call a README file for the data file that comes out of the experiment. And indeed, Gregor Wies's experiment has a README file. But when we're doing statistics, we also allow ourselves to use measurement incompatibility in the classical sort of way I've suggested. So we have classical mechanics, we've added noncommutativity, we've added quantum noise. We now have these two types of description. We shouldn't be talking about quantum systems and classical systems. A system is just what it is. We have our two different types of description, which we can use either, whichever is more useful for a particular experiment. If we do that, there's no such thing as non-classicality if we do allow ourselves to use CM+. But quantum does mean something. It means that the Planck's constant can't be ignored. We can't set Planck's constant to 0 and use a simpler mathematics. And that is how we distinguish a quantum experiment from a not quantum experiment, I suppose. Now, this is the part 3 that I won't talk about now. What my reading of the literature is for quantum and classical is that they have been converging in very many ways. And what I've attempted to do today is to give some indication of how I think that might look in 5 to 10 years' time. Thank you very much.